This is a presentation on control of wheeled robots. The explanation is based on simulation experiments utilizing simulation environment. Let's assume we want our robot to reach a certain point in 2D space. We could simply model the robot's trajectory using simple trigonometry and apply wheel movement without consideration to actual position. This is called open loop design. But what would happen if there was some uncertainty about robot's position? As we can see from the animation on the right, the robot drifts unpredictably. If our disturbance is always the same, i.e. it is not random, we could model it into our trajectory. In the experiment, I manually adjusted the parameters for wheel speeds to obtain near-perfect trajectory. This was only possible since uncertainty is very small. To account for uncertainty in the system, we need some sort of feedback about robot's position in the 2D space, and a way to account for the drift, which is what we call a controller, and the system a closed loop. In reality, uncertainties may come from a number of factors. The motors and electronics are non-ideal systems. Wheels may slip on the ground, or the assumption about our environment may not be correct, if the ground is uneven, for example. P or PI controllers are used. The P or proportional term simply applies a coefficient to the error. The I or integral term integrates error values over a length of time. It also has some coefficient attached to it to define its strength. The two outputs are summed to produce a control signal which is interpreted by the system. The controller's duty is to try to reduce the error to zero. Using P controller alone has its limitations. As we can see from the animation on the right, the P controller performs well to reach desired position. In fact, it reaches it very fast. However, it quickly deviates from it since there is a steady state offset. PI controller improves things by having determined steady state position. As we can see, the robot in the simulation quickly reaches near desired location and then slowly approaches it. The downside of integral term is that the system becomes significantly slower. Also, designing PI controller to be stable is difficult. From the diagram on the right, we can see how the simulated controller is working to reduce error to zero. In theory, we can make rotational P controller value very high, such that the robot turns instantly to the desired position. However, in practice we will notice that the motor in the robot has limited amount of torque and will not be able to change the speed that fast. This means that the robot will not follow our model. And if we consider what would happen with something like a service robot carrying trays, if it was made to simply rotate as fast as possible, it would make items fly off. Therefore, we may wish to design a controller for required behavior. P-value in rotational controller is lower to reduce the turning speed.